MathCAD than MATLAB to do a lot of stuff for your calculator, and you'll see why in a second. What I'm going to do before I get to this homework, I've got to go to, I've got to use this secure CRT thing. There's so many, there's two-factor authentication that I have to use a lot of times, and then I have to use secure CRT, and there's one other thing I have to use, this VPN client, if I want to do anything with any university software, and you're probably finding that out too. And then I have to go to, where is it? Activate. Can you all see the screen with MathCAD on it right now? You're seeing the shared screen? Okay. If you ever do use this, the server is delta.eng.auburn.edu. And then it takes a second. But anyway, come on. No, don't do that to me. You'll see why this thing is so nice. And you can download the freeware version. And then if you, you could contact Network Services, Shannon Price, and he'll tell you how to get the FlexLM license. Does everybody know what a FlexLM license is? Like for MATLAB, you have to, if you're using a university product, the FlexLM license is signed out from Auburn, and it interacts with your computer to allow you to use software from Auburn. You all use MATLAB, don't you? Right? Octave works about this. Are you familiar with Octave too? Or not? Octave is free. It's not quite as fast or as powerful as MATLAB, but it's identical in terms of its functionality and the coding, except for, I think, a couple of commands are slightly different. But Octave is real nice too. Sorry it's taken so long, but this thing, I had it up and I had it configured, but it doesn't work. Anyway, I'll just tell you, if you happen to be using this, and you'll see why it's nice. It doesn't have a built-in symbol for pi, so you have to use this WYSIWYG thing and tell what pi is. Now, for the characteristic impedance, like for the first problem, what was R prime for the first problem? Can somebody tell me? Just tell me. Anyone? Did you all see the homework? You all got it, right? On OneNote? How many saw the homework on OneNote? Thumbs up if you have. All right, you saw it. What's R prime? Just tell me.
It was 2.37 ohms per meter, I think.
2.37? Milliohms, maybe. Milliohms or ohms?
Doesn't look like there's milliohms, at least in the answer.
Well, let me see what that's a lot. Where the heck is it? My gosh, you're right. All right. So 2.37, and then what is L? I mean, what is I'll call it XL. The impedance for the inductance is what? 1J times something. What is it? What is omega L for that? Anyone? Can you see it? Tyler?
87.
Is that 87? If you can confirm that, that's great. And what's XC? It's equal to what? Minus 1J times, go ahead, just tell me.
For which part?
XC, the capacitive reactance, it's going to have 1 over omega C equal to something. Let me.
I see the omega C. I don't see the 1 over.
Well, what is omega C? What the heck is it?
0.252.
0.252. And sorry, give me 1 second here. And what is G?
7.63 microsiemens per meter.
All right, I'm doing this for a reason because I'm going to show you how these calculations are so easy to do here, and it pops the information out so quickly. Now, Z naught, this is the characteristic impedance, is equal to the square root of, then it's going to be R, I'm just going to call this R, plus, and it's going to be XL, right? And it's divided by G plus XC. And again, I didn't put the J omega L's in there, I just did. Now I'm going to have to go up here and change the R prime. I got rid of the primes because they're just irritating. Now this is going to be the magnitude of that. Or sorry, that's real and imaginary. If I want magnitude, it's just the magnitude bracket. That's that. And if I want the angle, it's argument of Z. Wait a second. This license didn't turn on for some reason. Hold on. Come on. I don't know why this thing's so slow right now, but I can't close it either. Now it's hung up. Sorry, guys. Try it again. First, this is on. All right, now. Well, while this is waiting to come up, I'm going to do this problem and out this way. They actually gave you some information, and they said that, first of all, I know Z naught is equal to the square root of R plus J omega L. I know these are per unit length resistance, capacitance, and inductance, divided by G plus J omega, or plus J omega C. Do y'all remember this class, how we did this last time? That's the characteristic impedance by definition. Now, what he does is actually give you some information that's related. First, he gives you gamma, right? He's going to give you gamma. And what, I can look this up, but what is gamma? Let me try to do this way. Shut that down. Open that. Move that over here so I can actually see the information. And then open my document cam. All right, they give you Z naught and they give you gamma. So gamma, I'll just leave gamma alone for now. It's 18.6 minus J.253. and they give you Z naught. They give you these two pieces of information, and they want the values of R, L, G, and C, and they give you a frequency of 100 megahertz or 10 to the 8th hertz. Are you with me on this? This is kind of a typical question. And with engineering, I'm going to say this, a lot of things you're doing is reverse engineering. You're trying to figure out some information based on observations. Here he gives you these two things, and he wants the values of R, G, L, and C. So if you take a look at this, well, what is gamma? Gamma is equal to the square root of R plus J omega L and G plus J omega C, right? Now, if I take a look at that right here, I know if I take this times Z naught, if I take gamma times Z naught, what I really have is what? Just, if you all see this right here, when I multiply this by this, can you see that the G plus J omega C terms cancel? I want everybody to see that. So you're left with, if I multiply these two together, I really have just R plus J omega L. Do you agree with that? Can you all see this? If you multiply Z naught times gamma, the 1 over square root of G plus J omega C here cancels the square root of G plus J omega C here, correct? Now, that's the first part. And then the second part is if we want G plus J omega C, all right, if we want that one, if I take gamma and divide by Z naught, what happens? Well, gamma is this, right? I'll even write it out. So it's R plus J omega L, G plus J omega C. And if I divide it by Z naught, it's 1 over this, or it's going to be square root of G plus J omega C over R plus J omega L, right? Everybody agree with that? I'm spending a lot of time on this for a reason. This is the one that usually fouls people up. And you can see what? The R plus J omega L cancels, so that's going to be equal to just G plus J omega C, correct? Now, I haven't put any numbers in, right? But what do you get from this right off the bat? You automatically get R and you automatically get G, correct? We'll do it in a second. But you all see that? When we do this, when we multiply these two numbers, whatever the value of gamma and Z naught are, we get R automatically and G automatically, right? Now, when I talk about omega L, we have omega, if we have F as 10 to the 8th, omega is 2 pi times 10 to the 8th, right? Are you with me? And if that's the case, automatically, when we have J omega L here, we simply divide that out by, we divide out the imaginary term by J omega and we get L. Do you all follow me on this, class? And likewise, if we divide the imaginary term in the division right here by J omega C, we get C. So this is a straightforward process once you see that the way to actually unmask the values is by multiplying and dividing these components, these numbers, right? Gamma and Z naught. Try to get familiar with that. We can put the values in, but I think for the sake of time, I'll do this at the end of the class if time allows. I want to see if my program came back up. I'm hoping it did. It's still not, never mind. I'll leave that alone. It's still not connected. Okay, next, let's see. The next one I want to talk about is the second problem. Here, I have the values of frequency, resistance, inductance, capacitance, and G. Calculate Z naught and the propagation constant, and assume 30 watts is flowing down the line. How much power is flowing at 3 meters? We're going to do this one now. Now, first of all, this brings me to where I left off last time when I talk about power. And I think you remember we were talking about power. Come on. when we talk about power, I did it this way. First, I said that if we're going to be talking about power, we're really talking about a transmission line that's got some length, and we're talking about power flowing. Average power flowing is a function of Z. Now, I'm just going to talk about power flowing in the plus Z direction. So this is the plus Z direction. When you take a look at the definition of power, this is average power. That's 1/2 the real part, V, and this is a phasor really, times I conjugate. I think this is where I left off last time. Do y'all remember this, class? You do. All right. Now remember, we're talking just about a positive going wave, and here V in general was equal to V naught plus, this is only a positive going wave, and it's e to the minus gamma Z, but that's also rendered as V0 plus e to the minus alpha Z times e to the minus j beta Z, correct? This is a phasor form of the voltage. Does everybody recall this, class? All right. Next, we also have a phasor form of the current. Now, the current for a wave propagating in the plus Z direction normally is written I0 plus e to the minus gamma Z, right? But we know two things. We know the ratio of V naught plus to I naught plus is equal to what? Anybody? Can anybody tell me what that ratio is? It's very important. The first problem was based on that information. Anyone?
Is it the impedance?
Characteristic impedance of the line. Can you all see this okay, by the way? I mean, is my camera on, by the way, or not? Can you see me, my face, or not?
Not your face, just the notepad.
This is weird. All right. I don't know why. It just shuts off for no reason. But anyway, back to this thing. Because of this, right, this is the characteristic impedance. The characteristic impedance is given as the square root of j omega L plus R. These are per meter quantities over G plus j omega C, right? And so it's got, in general, it's a magnitude and an angle. It's a complex number. We can say that I naught is equal to simply V naught divided by Z naught. So we say it's V naught plus over Z naught times e to the minus alpha Z, e to the minus j beta Z. I have to talk about one thing right here that's going to be important. Now, focus on this right here. Remember, I told you that Z naught in general is a complex number. So Z naught has actually got a magnitude of Z naught, and it has a phase angle, and has a phase angle e to the j theta of Z naught. Does everybody follow me there? Complex numbers are magnitude and angle, or real and imaginary, right? With me so far? Now, this is I in general, but Z is not in terms of a magnitude and angle, so I'm going to go ahead and make it a magnitude and angle. I'm just going to put a magnitude there, and the angle's downstairs, so it's e to the j theta Z. I'll just leave it at that. You all follow me? I put it as a magnitude and an angle, correct, class? Now I have a question. And please feel free to interact. It's the best way to learn is being interactive with the person. So now I'm going to ask you this. What happens when I have e to the j theta Z and I take it upstairs from denominator to numerator? What changes? I'll ask you a very simple form of the question. If I had 1 over 2 at an angle of 30 degrees, what happened? How can I render that another way? Isn't that really 1/2 at an angle of minus 30 degrees, class? Aren't you all with me? So what happens, I'll take this upstairs and it would become e to the minus j theta Z. Get rid of that. Y'all follow me? Can you all see this?
Yes.
All right. Now when I have this, I'm going to rewrite I naught, or I. I itself is now rendered as some V naught plus, that's a strict magnitude, by the way, over magnitude of Z naught. And then I have e to the minus alpha Z. And then I have this, which is e to the minus j. And here it's going to be beta Z plus theta. So it's beta Z plus theta. Or I can write it as simply I equals V naught plus over Z naught magnitude, e to the minus alpha Z, e to the minus j beta Z, and e to the minus j theta. Remember, this is the phasor form of a wave propagating in the plus Z direction. This is the current, actually. Now, the rule says to get average power, it's the real part of V times I conjugated, right? Do you remember this from your course in circuits, what power was? It's voltage times the conjugate of current. You take the real part of that and divide by 2, right? And the reason you divide by 2 is that these values, voltage and current in the phasor form, use the peak value of the voltage and current, not the RMS value. Are you familiar with RMS, the root mean squared value? That's, or sometimes called the effective value. All right, when we conjugate this, what happens? If I want to take this and conjugate it, what would happen, class? Would anything happen to the minus alpha Z? No, because e to the minus alpha Z is strictly a real number, isn't it? But what happens? The sign on the J here would change, and the sign on the J here would change, wouldn't it? Are you all familiar with conjugation, class? Conjugation just does what? It changes the angle from a positive to a negative angle, correct? Okay. Now, when I take this, the conjugate, and multiply it by voltage, I'm going to do it in the next page. When I go ahead and I have a voltage equal to V0 plus e to the minus alpha Z times e to the minus j beta Z, right? And then I have my current is V0 plus over the magnitude of Z naught times e to the minus alpha Z. Now, remember, I'm going to put the conjugate of the current here, e to the, then it would be j beta Z positive, this angle's positive, times e to the j theta Z, where this theta is the angle associated with Z naught. And I multiply them, what do I get? I get average power at the point Z is equal to 1/2 the real part of this voltage, V naught plus e to the minus alpha Z, e to the minus j beta Z times I conjugate. So then I get a V0 plus again over the magnitude of Z naught times e to the minus alpha Z, e to the j beta Z times e to the j alpha Z, theta Z. You all agree with that? I simply rewrote the conjugate of the current and the voltage inside the definition of power. Follow me, class? If you're with me, just the thumbs up is a good thing for me to see, if you understand. Y'all with me? All right, what do you see canceling here? I want you to take a look. It's important you see what happens. What happens to this e to the minus j beta Z and e to the j beta Z?
Cancel.
Sure they do. Add the exponents. So e to the minus j beta Z plus e to the j beta Z is e to the 0 or 1. So those things just remove themselves. Now, V naught is a strict real number, and magnitude of Z naught is a strict real number, and e to the minus alpha Z is also a strict real number. But what is e to the minus alpha Z times e to the minus alpha Z, class?
E to the minus 2
That's
alpha
right.
Z.
That's right. So I'll get rid of 1 and just put a 2 there. Now I can say this whole thing, P av, a function of Z, is really equal to 1/2. Then I can, since it's the real part, these are all real numbers, so I can take V0 plus and square it. I can divide by magnitude of Z naught. Then I can take the e to the minus 2 alpha Z outside. Now, one last step is I need the real part of each of the j theta z, right? And I put Euler's identity down last time, didn't I? Class, you all remember or not? All right, Euler says what? If I have e to the j theta, that's equal to cosine of theta plus j sine of theta, right? The real part is just cosine of theta. So the real part of e to the j theta would be the cosine of theta associated with z. And this is the actual power flowing down a line at any point. Are you with me? Now, in the actual problem I gave you, I gotta see if I can pull that up.
What's in the parentheses on that cosine?
That's the angle theta z. It's the angle associated with z.
Okay.
With z naught, the characteristic impedance. And please ask questions if you don't understand something. It's the only really good way to learn, is to ask questions when there's a problem. So with this particular problem, I give you some information about how much power is flowing down, and I give you information about frequency and all the parameters for L, R, G, and C. So we'll do this one together, and hopefully I can activate this license. That, or I'm just going to use Octave. I'm not full with it. Now this thing should change, but in the meantime, oh no, is this thing not responding again? I'm gonna have to shut it down. I can. I'll use Octave. This is about the same as MATLAB, and I think everybody here has used MATLAB, correct? MATLAB is going to be essential for everything you do. And did it come up? All right, so this is Octave, and matter of fact, let me do this. M files are called scripts. Here's what I normally do when I do these things. Try to. I always put clear all and then close all. And then CLC. In MATLAB, it clears the screen, gets rid of everything in memory, and it shuts down all the plots. So you have a fresh thing. Then you put the values here that you're going to be using. So R per meter in this one is 1 milliohm, so 0.001. Then C is equal to 2e to the minus 12, that's 2 picofarad. And then L was 1e to the minus 6, right? And G is equal to 0, which is nice. Then I have F is equal to 10 to the 8th, right? Or 1e to the 8th. That should do it. And then omega is equal to 2 times pi times F. And after that, I have to define Z naught, So Z naught is equal to SQRT of R, well, actually R plus 1J times omega times L over G plus 1J times omega times C. And then I have to define gamma. Gamma is equal to a square root of R plus 1J times omega times L times G plus 1J times omega times C. Wait. I'm going to put another bracket right there. And that's gamma. And now I'm going to just run these for a second to see if I've made any mistakes. So in the command window, these are the answers for Z naught, and that's the answer for gamma. And I'll put them in here, down here. I don't know why that's there. And this is problem 4, or no, problem 3. And then here, when I go back to the editor, I can say alpha is going to be equal to the real part of gamma. Remember, gamma is equal to alpha plus J beta. And so if I run it again and go to the command window, I got an error. It might be RE. This is there's slight differences with octave, and this might just be RE. Oh, real. That's probably what it is. So that's alpha, and you can just see it's the real part of gamma. Y'all with me so far? Now, remember, power flow in general is equal to this equation right here. Sorry. This is power flow in general, right? Y'all see this? I want to recast this slightly differently. You see this term right here? That's really the power that's flowing when Z is 0. At 0, you would have this much power times the cosine. So P av of Z can really be put down as P0 times e to the minus 2 alpha Z, where P0 is equal to 1/2 magnitude of V naught plus squared over Z naught magnitude times cosine of theta Z. Can you follow me, everyone? Can you all see this okay? Oh, Ben, are you recording?
Yes, I am recording.
Thank you. And did everybody, was everybody able to view his, the video of the last lecture, if you looked, class? All right. So, and if there's any problems with the video or the audio, let me know, because I've got to know that in order to try to correct it. Now, back to the problem statement. It says, if you all have your homework, it's good to just look at this right now. It says that the assumed 30 watts is flowing at Z equals 0. How much power is flowing 3 meters down the line? All right, that means we have this 30, right? We have alpha, correct, class? So therefore, if we looked at P Av at Z equal 30, or any value of Z for that matter, that's just P0 e to the minus 2 alpha times 30. And that's the next thing I'm going to do over here. So now I come back to my editor. I hope you don't mind me doing this here. I like this because that way you see every single facet of the problem. And I'm just going to say P0, capital P0, is equal to 30. Could be anything, right? And by the way, when you put the semicolon, how many people know what that does? Anyone?
It stops it from outputting the result of that line.
Yeah, it won't keep reappearing. And that's a thing in MATLAB that gets irritating. If you have like I equals 1 to 500 or something like that, then all 500 values pop up. Then I'm going to say that P, and I'll just call it P30, capital P30, here is equal to, it's really going to be equal to P0 times EXP minus, and this is 2, remember the 2, times alpha times, and I'll just put Z here. And above here, I'll make Z equal to 30. Didn't it go? Oops, sorry. So it's 29.999 because it's so little attenuation. Y'all see this? All right, now back to this thing in the editor. Now I'm going to change a few things. All right, now I'm going to let R go down to 0.1 and see what happens. $29.87. $28. $19. You can see that as you change the value of R, less and less power is flowing past the point at 30 meters down the line. And this is the amount of power that's flowing past that point. It's being dissipated in the line prior. Do y'all follow me, class? With me? All right. So I'm trying to work that problem so you see all aspects of it.
Professor, I have a question.
Go ahead.
When it says like Z is 0, the impedance is 0, why did you put Z equal to 30?
No, that's not Z, that's the power, isn't it? Look at the actual equation right here. Power, right, is equal to P0 is this, P0 e to the minus 2 alpha Z. You see they say 30 watts is flowing at Z equals 0?
Mm-hmm.
That's this right here. The characteristic impedance is this, but it's not even needed here because we've given the power flowing down the line. We're not given the voltage of the current. Do you see that?
Mhm.
So when I did this right here, the only thing I'm doing is I calculated Z naught, I didn't use it. What I did is use the real part of gamma, which is alpha. That's what I needed for this calculation because I was given P naught. Can everybody follow me on this one? I'm going slow and just showing you how to use Octave. It could be, you could use MATLAB for this as well, or MathCAD, or any other, or Python if you use Python. Everybody with me? Now I'm going to continue on. The other problems are pretty well laid out for you right here. The last one is just straightforward. And this is just getting familiar with transmission line quantities and how to calculate characteristic impedance. But now we're going to move on to a few other things. And first thing we're going to do is talk about terminated lines. And I'm also going to actually mention one other thing first before I jump out of that or jump into that. All right, now, when we talk about power in a lot of quantities, usually what we do is talk about the actual, we talk about power flow in dB. Are you all familiar with the term decibels, class? You've heard of decibels, right? In general, this is an important thing to know. When we talk about a decibel, it's used for measuring quantities where there's many, many orders of magnitude change in the quantity's value. So what it actually is, a dB per se, is given as 20 times the log of the voltage, or this is dB voltage, or if we talk about dB current, that's 20 times the log of I, and it's magnitude, by the way. And if we talk about dB power, it's generally 10 times the log of the power. This, the magnitude of the power. Now, the reason it's 10 is because power is proportional to voltage squared or current squared. And something else, the dB loss of the voltage per meter is the same as the dB loss of the current per meter, same as the dB loss of the power per meter in a transmission line. That's another reason they use dB. It's irrelative what quantity you're talking about. The amount of decibels lost per meter are the same. And you've heard about this probably in your laboratories, the quantity dB, right? Yes? No? How many have heard of dB? I mean, just give me a thumbs up. Just let me know that. You have. Okay, good. Now, these are the general quantities. When we talk about dB, there's a couple of things that are important. There's volts in dB microvolts, and that's 20 times the log of the voltage, magnitude of the voltage, divided by 10 to the minus 6. What happens is a lot of times we talk about things that are referenced to something else or ratio to something else. dB microvolts takes the voltage and divides by 10 to the minus 6, because 10 to the minus 6 is a microvolt, correct? Then there's dB, these are the most common, well, actually, it's going to be power in dBm. And this is a very common one, power in dBm, and that's 10 times the log of the power divided by 10 to the minus third. The M signifies a milliwatt. This is a very common term. If you have phones, I mean, if you look at your phones and you'd have to fuss with them a bit, but look up how to read the power received, the power, it'll be in dBm in your phones. You can do that on any smartphone, like this smartphone I have. It's kind of nice to do that because you find out what your signal strength is at the point, and you'll realize when you go below about minus 100 dBm, you can't get any signal. Now, in the problems that you're going to be doing, they'll talk about how many dBm of loss occurs, and this is typical. So if you have a transmission line, like so, and there's power flowing on it, what they'll do is have alpha of the transmission line, not given in terms of Napier's per meter, but they'll give it in terms of dB per meter. You all follow me on this, class? Yeah.
Can you slide the paper down,
Oh,
please?
sorry. Thank you very much. So if you're talking about a transmission line, alpha, if you just do the calculation for alpha, come on, it will be in Napiers per meter using the quantities that I've gave you. But many times it's given in dB per meter for loss. Now here's the relationship between a Napier and the dB, and here's how you get it. In general, power is some P0 e to the minus 2 alpha z, correct? Right? That alpha is in Napiers per meter. And it comes from the calculation of the propagation constant. But if I take 10 times the log of the power right here, that would be 10 times the log of P0 e to the minus 2 alpha z. Then what happens is you get, that's equal to 10 log of P0. And then you have plus 10 times log of e to the minus 2 alpha z. Now, this term is a static constant. This would be power in dB. And it's not dB, I'm just dB. But one thing you can see, this is a constant. And this is something that's a function of z. I'm going to go ahead and complete that. Remember, log of e to the anything, it allows you to take out the anything in front of this. So really, this is going to be 10 times the log of P0 minus, and then it's going to be 20 times z. Well, I'm going to put 20 times log of e, and then it would be times alpha z. You still have to take the log of e here. Now, what you're going to see, if you have calculators, you can go do it. Y'all see what I'm doing? I'm just going ahead and mathematically doing the log of this. So if I take a log of e to the minus 2 alpha z, the minus 2 alpha z come out in front. And I'm going to take the 2 and lop it in here with the 10, so I get 20, and I make log e by itself. This number is an interesting number because that is 8.686. So this is 10 times the log of P0 minus 8.686. You can go ahead and do this on your calculators, prove it to yourself, times alpha z. And that's power in dB. Now, if we want the power loss per meter, and here's the important part. Alpha is in Napiers per meter. Alpha given in dB per meter is the most common way of expressing it. So what we do is let z just go to 1. And then when we take a look at the rate of change, it's simply going to be this. So power in dB per meter, or I'm sorry, alpha in dB per meter. And the way you get this is, I didn't express this quite right. You take the power at z equals 0. Well, this term goes away right here, and you just have this, and then the power 1 meter down the line, and that would be this, would be subtracting from it. You would put z equals 1. But what happens is that the amount of dB loss per meter would just be minus 8.686 times alpha. So that means alpha in dB per meter is really going to be 8.686 alpha in, this would be in Napiers per meter. This is a conversion. So if you're given alpha, say 4 dB per meter, and you wanted to know what alpha in Napiers per meter was, you would take the 4 dB and divide it by 8.686. Y'all follow me in this class? This is the conversion. If you looked in the book, you saw alpha given, right? In terms of dB per meter and in terms of Napiers per meter. How many understand that? Just a thumbs up if you can give me. You all with me? All right, it's straightforward. You can go through it yourself. It's very straightforward. Now, after that, we have to talk about terminated transmission lines. I wanted to make sure I mentioned this power conversion for alpha because it's used all the time. So I'm going to get a new piece of paper. By the way, if you have questions at any point, just jump in and ask. You don't have to wait until there's a pause. So now the next thing is, if we have, this is terminated transmission lines. If you have a book, you can just follow along in the book. But if we have a transmission line like such, and then we got some load here, this has some characteristic impedance. I'll put a source on here too. I'll go ahead and put a voltage source right here. Now, what happens when you terminate a line is this. It's just putting like a resistor at the end of it, or an inductor or capacitor. You're going to have propagation of electromagnetic waves down the line, the voltage, and then once they hit there, they'll reflect back, right? But because this thing has got a finite length, they'll ricochet back and forth, and there'll be a steady state pattern that occurs. I'm going to try to explain this as simply as possible. Just think about a rope, right? If a rope was infinitely long and you shook it at one end, the wave would theoretically travel all the way down the rope, right? But if you take that rope and you tie it to something, that would be fixing the actual height of the rope, or the actual displacement, and you shook it, you would get standing waves on that rope. There would be reflected and transmitted waves. It would form a pattern. The rope would show itself to have like nodes where there's no displacement change. And there would also be places where there's large displacement. Do you all follow me in that class? The analogy, you've seen this in physics, I'm sure. That's the same way here. So in general, because we'll assume this is the z direction, and we always put the load at z equals 0, and that you do this for mathematical reasons, then I can say, if I have a voltage here causing a voltage down the line here versus z, I can express the voltage on the line as some V0 plus e to the minus gamma z plus some V0 minus e to the gamma z. And I can express the current I of z equal to V0 plus over Z naught times e to the minus gamma z plus V, actually this is minus V0 minus over Z0, and I'll put Z0 plus here, times e to the gamma z. Now, you're familiar that V naught minus is simply equal to the magnitude of the negative traveling wave, right? Remember last time we talked about that? And V0 plus is the magnitude of the positive traveling wave. Well, since you have both, you have to include both terms. So here's a couple of things that come out of this, and I want you to pay attention. This is real important. When I'm looking at this equation right here, I know the voltage that's going to be at the load, right? At the load here where z equals 0, V at the load, or at 0, will be equal to just V0 plus V0 minus, right? That has to be, because I put the load at 0. That means this values of z are actually negative, right? Are you with me, class? And I can furthermore say that I'll make this transmission line have a total length of L as such. Now, the next thing we're going to do is say, well, what was I at 0? This is at the load. Well, I of 0 would just be V0 plus over Z naught plus minus V0 minus over Z naught plus, right? Because the e to the 0 is 0, and we're going to do this at z equals 0. I mandated the load be at z equals 0. Now I have these two quantities, right? I want you to watch this. Do you all agree with me that that's the voltage and current at the load by definition? Correct, class? If z is 0 at the load, I've located the load here at 0. And in your books, if you want a picture of it, this is on page 49 if you have your books. Okay. It's just this, is what I'm showing you. So if we take the ratio of V0 to I0, by definition, what you're doing is taking the voltage and current relationships right across the load, right? And that has to be equal to the load impedance, ZL. So ZL would be V0 plus V0 minus over V0 plus minus V0 minus this whole quantity times Z naught, because you have 1 over Z naught there. And that would be ZL. Now, remember, that's the load, that's Z naught. Now what I can do, and for sake of time, I'm not going to monkey around with this thing too long. I could rearrange this. First thing I could do is divide everything by V0 plus. And in doing so, I'm going to do it right here. This term would become V0 plus over, I'm sorry, divide by, yeah, V0 plus. It would be, when I divide V0 plus by itself, I would get 1 plus V0 minus over V0 plus. Then it would be over 1 minus V0 minus over V0 plus times Z naught equal to ZL. Do you all agree with me? The only thing I'm doing, I'm showing you right here. I'm taking this quantity, this relationship, and dividing everything by V0 plus. Top and bottom of this equation by V0 plus. Sorry, just this side. So I get this. Do you all see that? Everybody? You can see this, can't you? All right. Now, I create a new quantity. It's called gamma L. And this is equal to the reflection coefficient, or it's termed the reflection. It's the reflection coefficient. And gamma L is simply V0 minus over V0 plus. So it's how much of the incoming signal that hits the load is reflected from the load. And what that's actually equal to, when you can manipulate this, we can solve for that quantity. That will be equal to ZL minus Z naught over ZL plus Z naught. Now this is one that's very important. It's the reflection coefficient at the load. And he shows you that on equation 2.65 on page 49. And it's very important. Okay? Now, remember that this, right here, this reflection coefficient is based on these equations solved, these two equations solved at the load. But if you wanted the ratio of the incoming to the outgoing, sorry, to the, for the positive traveling versus the reflected wave anywhere on the line, this is on page 50. Here, we could say that the reflection coefficient at any point Z would be equal to the reflection coefficient at the load times e to the j, and then it would be, well, he doesn't use j, he has the complex one, so I'll do it his way. It's really e to the 2 gamma z. And I want you to take note that this will be negative because the load is located at z equals 0. Everybody follow me? How to get gamma L, right?
Professor?
Yeah.
Could you go back to the definition of gamma at the load real quick?
Yep, I'm gonna. Gamma of the load is equal to ZL minus Z naught over ZL plus Z naught. Do you have a book with you?
Thank you. It'll be here tomorrow, actually.
All right, well, that's on page 49, equation 26.65. This is the definition. I'm gonna make some comments about this. If you have a transmission line, right? And here's my load. And I'm taking a look at how much is going to be reflected off that. Well, what's the value of gamma L if I have Z load equals Z naught, the characteristic impedance? What is it? Just take a look at the equation. What happens if the load impedance is equal to the characteristic impedance? Just look. What's the value of the reflection coefficient, class? You can turn on your mics, you might as well. Anybody?
Is it 0?
0, yes, and that makes sense because effectively what happens, if Z0 is here, it's like the transmission line is going on forever, isn't it, class? There's no change in the characteristic impedance. You'll have no reflections. By the way, that is a goal whenever you build circuits to transmit power or communicate a signal. You always want impedance matching. You've heard that term before, right? Impedance matching is critical for proper behavior. Now, what happens if ZL is equal to 0 or a short circuit? What is gamma L? Just do the math. What happens if ZL is 0? Look at it. What's the value of gamma L?
-1.
-1. That's a condition you don't generally want. It's extremely bad. Another thing you need to find out is what is gamma L when Z0 is infinite or an open circuit? When you have an open circuit, there's nothing connected, correct, class? Well, what's the value when Z0 is going to infinity, or Z load's going to infinity, not ZL? When Z load goes to infinity, what is the value of the reflection coefficient? Do the math. When the load is tending to infinity, what happens?
1.
It's 1, right? And those are the three extremes where you have a perfectly matched circuit. This is called perfectly matched right here. You'll be hearing more. You get no reflection. That's what you strive for most of the time. If you have a short circuit, you'll get -1. If you have an open circuit, +1. These are all things that we'll see are very important calculations. Now, there's one other thing we like to do when we have this kind of stuff. We'd like to calculate what the impedance is right at the beginning, right here, right? I'd like to know what the input impedance is there for a length of line L. Correct, class? Now, how would you actually get how would you come up with a method for doing that if you were an engineer? Well, Z is always a ratio of current to voltage, isn't it, class? Impedance is always a ratio of the current to the voltage. So with that in mind, matter of fact, let me do one thing. This thing's bugging me over there. There, you can at least see me a little bit. When I take a look at this, if I want the input impedance here, and this is in your book on page 51, I think, what I would do is say that Z in as a function of Z. Remember, this is at 0, the load is at 0, this is positive Z here. So this distance would be actually Z equals -L, if I'm right there. Follow me on this? That would be equal to V0 plus, and then you would have, this is the other thing I've got to tell you. Because we got the reflection coefficient, before I get back to this, let me just mention this. Now our equations for V0 plus, or I'm sorry, our equations for V of Z are equal to V0 plus, and now it would be e to the minus gamma Z, and then you can put the reflection coefficient at the load in here times, remember, reflection coefficient at the load times V0 plus is V0 minus. Okay, you can replace, instead of putting V0 minus here, you put in gamma L times e to the gamma Z, and you can write I of Z equal to V0 plus over Z0 plus times e to the minus gamma Z, and here it would be minus gamma L e to the gamma Z. So these are the equations for voltage and current with V0 minus defined as V0 plus times gamma L, because I know you just saw this, so I'm going to rewrite it. Gamma L is the ratio of V0 minus over V0 plus, or V0 minus is gamma L times V0 plus. So I've rewritten those equations in terms of the reflection coefficient. Does everybody understand this, class? With me? Thumbs up if you are. Hang in there with me, all right? I want to cover a little more ground. All right, now I have this here. If I wanted the impedance, this is really going to be the ratio of voltage to current. Well, this is the voltage, e to the minus gamma Z plus gamma L e to the gamma Z here. And this is the current, so it would be V0 plus again. And then it's e to the minus gamma Z minus gamma L e to the gamma Z. And since it's divided by Z naught, you can put Z naught up here. I'm just showing you what happens when we calculate input impedance. That's the ratio of current to voltage at any point Z. Now, y'all see that the V0 plus cancels. And well, it should, because impedance should never be a function of voltage. It should just be a function of the ratio of voltage to current. Really, it should only be a function of the parameters on the line, never a function of the source voltage. When I take a look at this equation, are you familiar with hyperbolic functions at all? Anyone? Do you know what I'm talking about when I say a hyperbolic function? Sinh, cosh, tan. All right, well, just for the sake of, I don't want to linger on this because it's not used very often. But a hyperbolic, if you have e to the, call it minus x, that's equal to cosh of x plus sinh of x. And really, let me do it this way. You remember cosine of anything is equal to really e to the j that anything plus e to the minus j that anything over 2. Do you all remember that? That's Euler's identity 1 of 3, right? How many remember this? If you have a cosine of, theta, pardon me. Cosine of theta is e to the j theta plus e to the minus j theta over 2. How many remember that? Okay, well, I'm going to put them down then because I can see this is important. Who can tell me what the sine of theta is in terms of exponential quantities? Anyone? Ben? You know? Tyler?
Don't know.
Is it Carlin? Do you know? Anthony? Okay. I'm going to just show you this. These you must know. By the way, I assume people know them. Now I can't make that assumption, so I'm going to show you. The sine is equal to e to the j theta minus e to the minus j theta over 2j. And we get these from this relationship. This is Euler's. J theta is equal to cosine of theta plus j sine of theta. Do you remember this one right here? The last one I wrote? How many remember seeing it at least? Just show of hands. These are very, very important. These are Euler's identities. This one we use all the time. We use these two. This is the cosine defined in terms of exponentials, and this is the sine. The reason I did that, I wanted to use these relationships to develop this relationship. But having said that, I'll just say one last thing. If this is the cosine of an imaginary, for an imaginary argument, it's really these things. Then the cosh, C-O-S-H of theta would be equal to just e to the j theta, e to the theta plus e to the minus theta over 2. In other words, you remove the j. That's called a hyperbolic cosine or cosh. And I'm not going to linger there, but what happens is this. To get the final form of the relationship, the quantities here, the e to the minus gamma z, remember gamma is what? Alpha plus j beta. It has real and imaginary parts, correct, class? Right? Gamma is the propagation constant. You go to and use hyperbolic functions to expand these, and then you sort of collect them. So I'm going to write this. I know I'm over by a minute or two. Just let me finish this thought, though. It's important. And I'm sorry I had technical difficulties in the beginning, but that sort of was on Canvas. All right, I want you to follow me on this. This is important. Zn, if we manipulated that, would be equal to the characteristic impedance Z naught, and these are on page 51, by the way, times ZL plus Z naught, and times the I had to cross that out, times the tan. This is a hyperbolic tangent of gamma times Z over ZL and, or I mean, sorry, Z naught, pardon me, Z naught plus ZL times the hyperbolic tangent of gamma times Z. And that's the input impedance at a location Z. And this is for lossy lines. Write that down. But for lossless, then Zn as a function of Z is equal to Z naught times Zn plus J, and there's a J there, Z naught, times just the tangent of beta. And I'm going to go ahead and just put in Zn of L. I'm going to save some time. Zn of L, beta times L over Z naught plus J Z load, this is load, times tangent of beta L. And I'm going to explain something here. That value L is going to be a strict positive number. Remember, Z would be minus L, but L is just the length in meters. And this is the input impedance. And this is the one we use over and over again right here. And I'll try to explain something about this. Is the input impedance to the line. So if I have a line, and there's a load here, right? The load is at Z equals 0, and the line has a length L. Then what I'm looking at is the impedance right here, Z in to the line. Got to tell you one thing, class. This is important. This equation on the top right here is very rarely used. And I'm just going to tell you that if you have a transmission line that has so much loss that you need to use this equation to describe it, you've got a very bad transmission line. Right? Just telling you that. We don't use this. This is the one we use all the time for our work. And that will give the input impedance at any point from the load. It's a very important equation. This is technically my office hour. Now, how many people have a class coming up right after this one? What time does your class start?
9:45.
9:45?
Yeah, 9:45.
And it's a Zoom class, right? So this is my office hour. I try to put my office hour right after my class, so I got everybody here and we can continue. Do you mind if I continue for a second? Just close and show you a few tricks on this one, all right? Remember, that's the input impedance, all right? With me? Now, I got a question for you. If you look at this, remember, how do you get beta? And here we're going to talk about lossless lines and how to get quantities. So if we have lossless, and you can put down low loss lines. Low loss is going to be like 0.1 dB per meter, but we'll talk more about that later. If we have lossless lines or low loss lines and we default to this equation, there's certain things you have to understand. If ZL is equal to 0, all right, if the load is a short circuit, then my input impedance, Zn, as a function of Z, or a function of L, better yet, as a function of L, equals Z naught. Now remember, the load is 0. So this term, the L here, ZL is 0. So I have J Z naught times tangent of beta L over, and remember, ZL 0, so this term goes away. And I just have divided by Z naught, correct? You all see what I'm doing? I let the load be 0. That means here it goes to 0, and there it goes to 0. Gets rid of that term and that term. And I have this. You all follow me on that, class? All right. You can see that these Z naughts cancel. So my input impedance is J Z naught times the tangent of beta L. And that would be the input impedance at a distance L away. What can you see happening to that? What if L is 0? What's the input impedance? If the length of line is 0, what is it? Well, what's the tangent of 0? Anyone?
0?
It's 0, right? And you would expect that. If this thing's a short circuit, here we have ZL, so this is a short. Well, if the line is, there's no line, you expect to measure a short, right? You expect that. But what happens? What happens to this when beta L is equal to pi over 2? Now what's Zn? And this is for really beta L equal pi over 2. What happens now? What's tangent of pi over 2 anyway? Think about it. Opposite over adjacent is straight up. It's infinite, isn't it, class? Come on. Tangent of 90 degrees is infinite. You all know that, don't you? I know it's early, but you got to help me out here. I'm feeling really like I'm dealing with people that are not quite there. All right. That goes to infinity. So that's important. When beta L is pi over 2, now the input impedance is infinite. Now think about this. Beta L would be the argument of the tangent function, correct? Well, what's beta? Well, we didn't spend a lot of time on this, but beta is 2 pi over the wavelength. That's beta. Do y'all remember that from physics? We did a little of this earlier. Do y'all remember when I went through wavelength, I went through a period. Do y'all remember that? Well, and we went through beta, what beta was. And if here beta is 2 pi over lambda, that's the definition of beta in terms of wavelength. And I guess I didn't develop this argument. But if that's the case, then beta L would be what? Beta times L would be 2 pi times, I'm sorry, if beta L equaled pi over 2, pardon me, that would be the argument, sorry. If beta L equaled pi over 2, then we could say L is what? Well, L would be equal to pi over 2 divided by beta, and that's pi over 2, and beta is 2 pi, right? And this is wavelength too, by the way. And that means it's lambda over 4. This is the important point. So when L is equal to lambda over 4, the input impedance to this line would be infinite. And this is the important thing I want to tell you. No matter what this impedance is, if I move a quarter wavelength away from it, this length here becomes a quarter wavelength. The impedance I read is 1 over that impedance. So if it's a short circuit, the impedance is 0. I move a quarter wavelength, the impedance would be infinite. Do you follow me? Are you with me on this or not? No?
Can we see the bottom of the paper? We couldn't see it when you were writing it out.
Yeah. What I'm going to say, I was just showing you that the length would be pi over, or lambda over 4 would be the length of line that would make the argument of the tangent pi over 2. But are you with me with this right here, class? So far, right? And if this is for a short circuit, so if you take a look at this, when L is 0, this is 0. It should be. You're measuring the load impedance. Well, when beta L right here is pi over 2, then tangent goes to infinity. Infinity, I'm measuring infinite impedance. Do you all agree with that? You all agree tangent of 90 degrees is infinite, right? Well, what is that in terms of length? Well, when beta L is equal to pi over 2, that means L is pi over 2 divided by beta, right? Now, beta itself, I could do this a couple of ways, but beta is really 2 pi over lambda. And I don't have time today, but that means L itself would be equal to pi over 2 divided by beta, which is 2 pi divided by lambda. And you can see the pi's cancel, and you get lambda over 4. And today I'm not going to dwell on this, but when you go a quarter wavelength away from the load, the impedance you're going to measure is 1 over that value of the load impedance. And that's very important. Now, I didn't have time to get into the voltage standing wave ratio, so I'd like you this weekend for sure to read pages 50 through 50, well, probably through 60. I'm going to give you some homework. And before I sign off, I know you've got other classes, but do you have any other questions at all? I'll tell you what I'm planning on doing. I'm going to get all your emails, and I'll create a group on Outlook so I won't have this mail problem with the Zoom link that I had today.